Okay, in this segment I show you how to read and write some files using both the text files and binary file formats. And this one should be fun. Type along with it as usual. We'll look at some specs that I'll just make up and do some reading and writing, and then you'll be on your own. It doesn't take long to pick this up. There's only that many things that you can do with reading and writing files. So let's go and look at a spec and we'll type some code to solve it. So let's look at our first spec. We're going to work with text files first of all, and not confuse text files with binary files. So the first spec, we're going to open a file for text writing, and we're going to put all of the text into that file that appears on this slide, and then close the file. And the first thing that I'm going to do is I'm going to make a place for the files to show up, so I won't have to be searching around for where the file is that I just created. That's kind of a frustrating thing to happen. So I'm going to go into the Windows Explorer, and in my computer on drive C, I'm going to make a folder called My Files. And My Files is an empty folder, and it's just a place that I'm going to use for dropping the files. Don't make a folder in My Documents, because the actual path to My Documents is fairly complicated. It looks like it's right there, but it's not. It's down in the C drive somewhere. So on the C drive, a new folder called My Files that has nothing in it, and you'll see how we're going to use that. So let's go to the development environment, and I made a program that does nothing except it runs, and it's called textfiles.c. So the first thing we have to do is to declare a file pointer, and you can call this anything you want, my text file. And then we're going to open the file. So my text file gets, and the function is fopen, and it pops up what we're going to have to specify. We're going to specify the name of the file. So the name of the file, we're going to include where the file is. So it's on the C drive, and it's in a folder called My Files. And I'm going to call this first text file.text. So I'm using two double slashes here. I mean double slashes, backslashes, and I hope you remember from way back in the beginning, if you put a backslash in a string inside of double quotes, that means that the next character is a special one. So if we want a backslash to appear in the string, the only way to do that is to put two. The first one means that the next one is really a slash. So it's like backslash n. It's not an n at all. It's an escape sequence. So that's one of the things that you might do wrong. We can use double slashes when we really want to specify the path to the file. We're really putting a single slash in there. So if you create a file that doesn't exist, or if you open a file that doesn't exist, and you open it for writing, so that's the mode that we're going to open this file, then it will create the file for us. And every time we open a file, we should check to see if it really worked. And fopen will return null if it didn't work. So these things, like null in all uppercase, and the function fopen, and the file pointer type, are all defined in standard I.O. So we don't have to do anything except say include standard I.O., and we have access to all of those. So if the fopen failed, then maybe it failed because we don't have access to write there, or if we were opening for reading, it might fail because we tried to open a file to read that isn't there. There are different reasons why it could fail. It shouldn't, if we get the path to the file correct. But if it does, let's output a message. We failed to open the file, and we're just going to stop the program. And we can stop the program by calling an exit function, and the value we put inside of the exit is kind of like an error code. If you had lots of different reasons why your program could fail, you might want to make up different error codes. So we should have a program now that will compile and run, and it will create a file out there. So let's try it. Let's just run this, and the program ended. Now I'll go out, and there it is, first text file.txt. It has 0 bytes in it because we created the file, we didn't write anything into it. So I'm just going to throw that one away. You don't have to. We could write over it, but I'm going to throw that file away, and now we're going to start putting some text into the file. So let's do an fprintf. Maybe I'll make a mistake and you'll get to see me correct things. So fprintf, it works like a printf, except the first parameter is a file pointer. So I've got a file pointer here, my text file. That's where I want the text to go. And what do I want to go into the file? Well, the spec said put the text from the slide into the file, and it said open a file for text writing. Open a file for text writing, put all of the text in the file that appears on this slide. And I'm going to close the file. Okay, so that program ran, and nothing came out on the console. All of these fprintfs supposedly put stuff into that file that we dropped. And let's double click it, and I didn't put any carriage returns. Look at that. So the text is in the file, and because it's a txt file, then Notepad will open it if you double click on it. And the file is closed because we closed it before we left. Maybe I should have put a carriage return here. Run the program again, go back, and make sure that, okay, so the carriage return is in there now. So we have a program that can open a text file, check to see if the open was successful. If it was unsuccessful, then fopen would have returned null, and then we just wrote some text into the file. Let's go back to the spec and see what we were supposed to do. Open the same file for reading, and then we're going to read one character at a time, counting how many of each vowel occurs in the text. So let's do the same thing again, almost. We're going to open the file, but this time instead of for writing, we're going to open it for reading, and then we will make a loop that will read the characters from the file one by one. Okay, so the first thing I'm going to do is I'm going to declare a character variable that will be used to hold the characters as I read them from the file. And now I'll make a while loop that says while ch gets, and the function is getC, and it takes a file pointer, my text file, and that input statement, get the character out of the file, will return EOF when we've hit the end. So I want that assignment statement, while it's not equal to EOF, and that is a defined constant, so we don't have to do anything special to use it. It's the same as null is a defined constant in standardIO.h. Well, I'd like to see if this is going to work before I do anything else. So maybe what I'll do is I'll just make a printf statement, and I'll say print that character out onto the console, ch. So I'm using a printf, and if I run this and it works, it should get each character out of the file and spit it out onto the console. And then for good practice, I'll close the text file, and let's build and run that and see if it does. It spits all of the characters that were in the file out onto the console. So I have a loop now that's reading the characters one by one, and each time it reads a character, it puts it in this variable ch. So maybe I'll leave that printf statement there for debugging purposes, even though it's not really part of the spec. And now my job is to add up how many of each vowel there are. So how many A, E, I, O, and U? I better declare a variable for each of those. So A count, E count, and since these are counters, I'll start them at 0. I count A, E, I, O. I don't think I'll count Y as a vowel. So I have a variable for each counter. Now I could make some if statements here that say if the character is equal to the character, single quote, the character A, then add 1 to the A count, and so on. But I'm going to do a little bit differently. I'm going to use a switch. I hope you remember how a switch works. We switch on an expression, and then inside of the switch we're going to make a case for each of the things we're looking for. So case in single quotes, an A. If you remember how a switch works, the case has to be a constant here, and it's supposed to be a number. It must be something that can be promoted to an int. Well, a char variable is an integer data type, and it's storing the ASCII code of the characters. So that is really counting as, that is a integer constant in case A. So I'll say A count plus plus, and then a break statement. And then I'll make the next case E count plus plus, the break statement, I, O. You have to put a break statement at the end of each case, or the flow of control will bleed into the next case. And in the default case, I don't want to do anything. So if I find any character other than A, E, I, O, or U, I am not going to do anything. So that's the end of the switch. We should be able to say there are A's in the file. Output A count. Similarly for each of the others. How many E's are there? Would be the value in E count. And so on. So I'll let you fill in the rest of those. And this one is complicated enough so that I'd like to watch this happen. So I'm going to set a breakpoint here, and I'm going to watch the file get read and see if my switch statement is working the way that I expect it to be. Okay, so we've opened the file, and we're going to execute this statement to read one character out of the file, and we got, what did we get? It looks like capital O. Is that correct? Is that the first character in there? And does that count as a vowel? Well, it should, even though our switch statement is not going to count it. Okay, so we found a bug already. So CH has capital O, and it doesn't match any of those. Aren't debuggers great? They show you what you did wrong just a moment ago. So the next character that we read is a P, and that won't match any of the cases. And the next character that we have is an E, and that should jump to the E case, and it does. So we found an E, we add 1 to the E counter, and break the switch, and get the next character out of the file. It's an N. You can look down here and see what's in the variable CH each time. So there's a space. There's an A, so this time switching on CH we should jump to case A and add 1 to A counter. Okay, I'm believing that this is working, so I'm going to set another breakpoint down here, and I'm going to turn this one off if I can. Okay, and now I'm going to hit F5 again. That will allow that loop to continue until it's done, and now that we've fallen out, we have 5 A's, there it is, 5 A's and 9 E's. 5 A's and 9 E's. And some carriage returns would have made that nicer. There are 5 A's in the file, there are 9 E's in the file. Is it right? Here's my file. How many A's are there? 1, 2, 3, 4, 5. Okay, I believe it. I think we have counted how many vowels there are in the file, and the mistake that we have is we only counted lowercase vowels. So here's how we're going to fix that. We're going to say uppercase A. So here's how the switch works. When it finds we evaluate this character, and then it jumps to one of the cases if it matches any. And we can allow it to jump to the lowercase a or the uppercase a, because the lowercase a case doesn't have any break statement. So in both of those cases, we will add one to the a count and then break. So let's repeat that for each of the other ones. Case capital E, case capital I, case capital O, and case capital U. And I have a build error. Good. Mistakes are good. Let's do compile and see what the compile error is. You should be able to double-click on the error line, and when recording, double-click doesn't work right. But it's telling me new line inconstant, so I've done something wrong with a set of quotes. Well, it's on line 32. We can certainly do that. That's line 44, 37, 28, 30, and of course it's something silly. Okay, so we've written a program that will open a file, count how many vowels, how many of each vowel there is in the file, and output the results. And I'm going to let you finish outputting each of the results. And we got to exercise the switch statement. So this was a nice place to make a switch statement. This is much cleaner than the 10 if-else statements would have been. So if you haven't used the switch statement before, the reason for having them is that when they are handy, when they're useful, they make much cleaner code. So this loop is very non-congested compared to what you might have if you used a bunch of if statements. So let's go back to the spec now and see what we're supposed to be doing next. So this time what we're going to do is we're going to open the file for reading, and we're going to count how many words are in the file. So this one is a little bit more tricky. We can't just read one character at a time. We have to kind of decide what it means exactly that there is a word in the file. When does a word start? When does it stop? And I think we'll just go in and try something and see if it works. So let's go back to the code, and we close the file that time, and we're going to reopen the file. I will just copy this line. So we're going to open the file. The file pointer will be back to the beginning of the file, and we will read from the file. So let's use an fscanf this time, and we're going to read from my text file, and we need to specify the format specifier. So if I put %s, what will that do? And we have to give it a place for the data to be read from. Okay, so we don't have a character array anywhere that we would put that text from the file. So let's go all the way back up to the top, and we will declare a character array. And what I'm hoping is that I'm going to ask for one word out of the file, and I'm just going to leave a whole lot of space for it so that I'm sure I won't run out. So one word, and I'm going to leave room for 100 characters, and I'm going to put word here. And you know that a scanf requires an address of the place where it's going to put the data that it reads. Remember that the name of an array is an address. So I declared a character array called word, and I don't have to put the address of word because the name of the array is already the address of the memory that I just allocated. And just to see what this is going to do, I'm going to put a printf statement in, and I'm going to dump out to the console the string with a carriage return that I just read. Okay, let's just run that and see what happens. So what I'm hoping is, well, no, before I do that, I'm going to close the file. I want everybody to be in the habit of if you open a file, then you should close the file. Okay, so that's the last message from the last example. There are 9 E's in the file, and we got one, it looks like one word, open. So when we use the %s, it didn't read the whole string, the whole line. It stopped when it came to a white space character. So now we want to make a loop of doing this. Let's just, before we start counting them, let's just read words and spit them out. And we have to know, when does fscanf indicate that it's at the end of a file? Or what does fscanf do exactly when it comes to the end of the file? So there are lots of ways. When you don't know what one of these functions is going to do, it's better to have some idea. I know it's going to be a little bit of a guess, but it's better to have some idea of what it's going to do. So why don't we go and look up the definition of fscanf and see what it returns, or how it indicates that you've come to the end of a file. So let's find out what fscanf does, and a good way of doing it is to just Google it. Or you probably have a book in front of you, but let's read about fscanf and what it returns. Well, it returns an int. It's complicated. There are a whole lot of format specifiers that you can use. Reading a text file can get really complicated. So we're looking through this file that we Googled on fscanf to find out what's really going on in there, and it's really, really long. This one function can do a whole lot of things, and what we're interested in is the return value. EOF is returned. If the input ends before the first matching failure or conversion, EOF is returned. It's not very easy to read these things and understand what they're doing exactly. So what we're going to do is we're going to make the same loop that we had before. So we're going to say while, and a lowercase w, while fscanf is not equal to EOF, and we're going to just spit out the word that we read from the file onto the console. So what I'm hoping is that the behavior of this loop will be to read one word at a time from the file. Okay, so there's the result of our vowel counting. Open a file for text writing. Put all of the text in the file that appears on this slide. So that seems to be working. Just a simple %s will allow us to read what we're calling a word, where a word is some characters that are white space delimited. And we need a word counter, and we're going to add 1 to the word counter for each word that we get, and we better go up and declare that, initialize it to 0, and output. This file has %i words. 19 words, is that right? It looks about right. Okay, so this was an exercise in reading information, writing information into a text file, and reading information out of a text file. There's a whole lot more we could have done with reading and writing text files, but this is what will get you started, and I encourage you to play with it, read the instructions for the functions you're using for as long as you can stand it, and then guess. But don't guess to start with. And when you are guessing something with these functions, walk through it in the debugger or put lots of printf statements so that you can see what's going on as soon as possible. Okay, let's go back to the slide now and look at input and output using binary files. Okay, so now we're going into the spec for reading and writing binary files. And here's the spec. We're going to open a file for binary writing and generate 1,000 random integers between 1 and 100, and we're going to write them into the file as they're generated, and then close the file. So let's go with this part first. Create a file for binary writing and put some random numbers in it, random integers. Okay, I've made a binary files.c project, and we're going to start from the beginning. it looks very much the same as it did the last time. I'll call this one bin file, and I'll open it fopen, and then let's specify where we want it to go on the C drive in my files, and I'm going to call it mybinfile.bin. So binary files typically end with .bin or .dat, not .txt, which is expected to be a text file. And we're going to open this file for writing in binary. WB is the mode, and then we will check to see if bin file, if it's equal to null, then we've got a problem, and we're going to output a message that says we've got a problem, and we will just exit with an error code of -1 if something has gone wrong. Okay, so let's seed the random number generator with the current time. I don't know if you remember how to do that or not, but that will just give us some interesting numbers. And I think we have to include one more file to remember what it is, time.h. And now we're going to do something 100 times. Okay, so we have a for loop that will go 100 times, and each time we're going to generate a random number. We'll generate the random number first. So we have a random number. It's said from 1 to 100 inclusive. So let's do modulus 100 plus 1, and we will write that number into the binary file. So I'm going to use a function called fwrite or frite, and fwrite, the first thing that we put here is the address of the data we want to write. So I'm going to say the address of random, and this function allows us to write a whole bunch of things at one time, as if we were writing an array of data. We're going to write, in this example, only one number. So the size of how many, the second parameter is how many bytes in each one of them, and it's going to be the size of int, and there's going to be 1, and the file pointer is bin file. And I've been typing for quite a while without actually compiling, so let's go and see what mistakes I've made. Build succeeded. That's pretty lucky. Okay, what is the size of an int? Do you remember? It's 4 bytes, so what we should have written into the file is 400 bytes. Let's close the file. I always forget that. And let's run this and see if there's a file in our directory called bin file. My bin file, there it is. And if we look at the properties of that file, we have exactly 400 bytes. So that's good news. You can't tell in the Explorer how many bytes there are. It just kind of says, well, there's a kilobyte. But if you do the properties of the file, then you'll get a more accurate idea of how many bytes you have actually written into the file. That's a good check for you. Now, what was the rest of this spec? We're going to open the file for reading, and we're going to read in all of the vowels, calculate their sum as they are read, and not using an array. And then we're going to find and output the average of the numbers. Okay, so we're going to open that file again for reading, read the numbers in one at a time, and find the average as we go along. Okay, I can take this line and change it. So we're going to open that file for read binary, and we're going to use a function called fread. So what are we going to read? We're going to read into an address. We can use the same number, the same variable, random. And we're going to read in 4 bytes, or the size of an int, one of those, and we're going to read it in from bin file. Okay, and that's what we need to do over and over until we come to the end of a file. So I know that there are 100 of them in there, and I could just read until I come to the end of the file, or I could read 100 times. And the spec also said we're going to calculate the average, so I have to sum them up, and then afterwards I'm going to say average gets sum divided by 100. So I need a double variable for the average, and we'll make sure that this is a double division, and an int variable for the sum. It's an accumulator, so we're going to initialize it to 0 and declare a place for the average. And the spec said to output the result. Let's put 3 places past the decimal, just for fun. What do you think the average should be of a bunch of random numbers in the range of 1 to 100? Well, I certainly hope that it's something around 50. And let's compile, see what happens. We're going to write the file, and then we're going to read it back, and the average 54.5. That's not too bad. Let's run it again. The average 49.8. Run it again. 53.5 roughly. So it does seem like we are generating random numbers, putting them into the file, and then reading them back. And I wonder how many of you noticed that after I was done reading the file, I neglected to close it. If you don't close the file, it will be closed for you if the program completes successfully. If your program crashes in the middle, which it often does when you're a beginner and you're manipulating files, then you've left the file open, and you can only have so many files open at one time, and that can cause a problem. You'll have to reboot the machine. It's not a big problem, it's just you can sit there scratching your head for a long time wondering why you can't open the file anymore that you were just able to open a minute ago, and it's because the operating system has used up all of its file handles. Okay, so I think we've got that part of the spec. We read the data back out of the file, summed it up, and output the average. Let's go back to the spec and see what happens. This time we're going to repeat the exercise using an array, and we're going to read all of the values from the file in one statement. Okay, read all of the values from the file in one statement. So this is a good way of showing you how powerful fread is, and we will read back all of the data in one statement. So we need a place to put the data when we read it back. So let's make an int array. I'll just call it all, and we want room for 100 of them, 100 ints. So we're going to open the file. Yes, that is the file that we just closed. We're going to close it when we're done with it this time, and this time we're going to fread, and we're going to read into the array I just made called all. Each one is size of int, and this time there's going to be 100 of them, and let's put the file pointer in file. I'm going to put a breakpoint here and run to that breakpoint, and we'll look at the data that's in the variable all. So here's our variable window, and here's the all, and we should have random numbers between 1 and 100, and there should be 100 of them. Okay, so think about how easy that was. I read 100 items out of the file. Each of them was the size of an int, and I put them all into this chunk of memory that I had reserved by declaring an array of 100 ints. I don't think you need to have more exercise on going through that array and finding the average of it. This segment is just on getting data out of the file. Okay, one more thing in this spec. Repeat the exercise above using an array. We just did that part, just for fun. If you seed the random number generator with 123, and then use Fseek to read the 30th number in the file. What is it? Okay, we have to understand what Fseek does. It moves the file pointer around in the file. So if we seed the random number generator with a constant 123, that means that all of us will have the same set of random numbers in the file. And then what is the 30th one? Let's see if we can do that. Well, instead of using the time for the random number seed, I'm just going to change it to 123. It's just a value I made up so that it would always be the same, so that the data will always be the same. So if we run this program now, the average is 49.33. If we run it again, the average is 49.33. And guess what? If we run it again, 49.33. So we have the same set of data each time. And now that means that all of us, if we use that particular random seed, should be able to use all of the same data. We should all be having the same data. So let's look at what Fseek does. Fseek will move the file pointer to a specific location. So Fseek in what file? In bin file, and we want the offset. So if we want the 30th number, what would the offset be? If we wanted the 0th one, the offset would be 0. If we want the 30th one, let's do 30 bytes, well, 30 times the size of an int. That's 4. So 30 times 4 is 120. So we would go to the 120th byte in the file, and then we can read it in. So fread, and we need a place to put it. I'll just put it in that random one. Random. Don't forget the ampersand. Fread and fwrite works with addresses. And we want one of them that is the size of an int, and we want it out of bin file. So what's being demonstrated here is we move the file pointer to any place in the file that we want and get something out of the file. So you can do random file access this way, and it can be pretty complicated depending on what's in your file. Ours is pretty easy, 100 ints, each of 4 bytes each. Just go to the 30th place and read 4 bytes there, and you'll have the 30th number in the file. Let's print it out. The 30th int is %i\n. We put it into the variable called random. So let's run to the breakpoint. Oh, there are build errors. That's good. You can figure out what I'm doing wrong. Fseek, too few arguments. Too few arguments. Fseek. Fseek requires that we specify the origin. Okay, where do we want to seek from? We want to seek from the start of the file. So I could put a 0 there. There are some constants that you can put there that say start at the beginning or start at the end. I can't remember what those constants are. So I'm going to go back and look on the slides and find out, or in Google, and find out what constant I should put in Fseek to indicate that I want to seek from the beginning of the file. And we find out that the possible constants are seek set, which means start at the beginning, seek cur, which means the current position in the file, and seek end, which means search relative to the end of the file. So let's go back in, and we're going to use, instead of 0, which would have worked anyway, seek set, and let's compile that and see if everything is working. Okay, and we'll run to the breakpoint, and it should have printed out that the 30th one is the number 15. Let's look in our array of data, all of the data from the file, and see if the 30th one is 15. That's lucky it is. Okay, so seeking around in a file randomly in a binary file turns out to be fairly easy. And this feels difficult to you, or it may feel difficult to you, because you can't open the file and see what's in it. So the file that we have over here that we've been writing, my bin file, if you open it with, suppose you open it with Notepad, what will you see in there? Well, a whole bunch of gibberish. Because it's not a text file, Notepad is expecting each byte to represent an ASCII code. And in this case, each 4 bytes is representing an int. So when we're opening that file in Notepad, we just see a bunch of junk and non-printable characters. So working with binary files turns out to be a little bit easier than working with text files. Remember how long the document was that would teach us how to use fscanf and all of the complexities. And fread and fwrite just take an address and how many of them do you want, how big is each one, and what file do you want it out of. It turns out to be much simpler. So here's the last spec. We're going to go and revisit the example on dynamic memory allocation when we made a struct representing a customer and we were dynamically allocating space for customer objects. The next thing we would like to do with those customer objects is put them in a file. So any business object that your program is using would have to be somehow persisted. That means written into a file or into a database, so that you then could open your company data and make reports from it or whatever you need to do. So we're going to go back and look at the customer struct, and I copied this out of the previous section where we were doing dynamic memory allocation. And I'm going to declare a couple of these customers. So let's make customer Bob and Susan, and that's a not dynamic memory allocation. Those are 2 structs allocated right there on the stack. So Bob's name is going to be, guess what, Bob, and that has to be a string copy, and Bob's customer ID is going to be an int 1, 2, 3, 4, 5, and how much does Bob owe us? Bob.amount owing is going to be $24.56. Let's do the same with Susan. I'm just making a couple of these structs so that we can write them into a file and then prove that it worked by reading them back from a file. Susan, how much does Susan owe us? She owes us $345.99. So she's going to be the deadbeat in the report, the deadbeats report. And let's make a file pointer for our customers. So a file pointer, customers. Remember that all of your declarations have to be up here at the top. When it stops looking like int, float, and double, you might not be thinking of them as obviously variable declarations, but all of these are data types, and all of these, like customers, is a variable, and they won't compile if they're mixed in with the rest of the code. So let's go and open the file. Customers is fopen, and we're going to put it in that same folder we've been using. And I'm going to call this one customers.dat, and we're going to open it for writing binary. And before I forget, I'm going to close it. It's always good practice to make sure that the fopen worked. I didn't do it in every example in the last video, or in this video in the earlier sections. If it is equal to null, then we've got a problem. So we'll say customer file failed to open. Give the user at least some clue of what had gone wrong instead of just ending the program. And now what we want to do is to write those customers into that binary file. So I'm going to use fwrite, and fwrite needs an address. We don't have an array this time, so we'll use the ampersand, the address of Bob, and how big is it? Well, it's the size of the data type, and the data type is customer. So I don't have to manually go and count up how many bytes there are. The size of will do that for me, so that fwrite puts the whole customer object in there, and we'll write Susan in as well, and then close the file. So I've been typing for a long time without compiling. That's not a good idea usually, but it turned out that it did compile. So we're lucky. And let's run this file, run this program, and go out and see if the file is there. There's the customers file, customers.dat, and how many bytes are in it? 112 bytes. So I wrote 2 customers into that file. I assume that each one is 56 bytes. Let's go back and check that. How many bytes in a car? Well, there's 40 bytes right there. There's 4, that's 44, plus 8 is 52. And why, then, is the file showing that each one has 56? Interesting. I don't expect you to know the answer, but it has something to do with byte alignment. So 40 characters here, when we actually wrote those 40 characters into the file, it did a byte alignment so that a couple extra bytes got put in there as fillers. So it didn't match exactly. We counted 40, 44, and 8 is 52, but the file had 56 bytes, so there are 2 extra bytes per customer object. Well, the issue with byte alignment and how many bytes actually go into the file is compiler specific, and you can also go into the compiler, into the IDE settings, and change how you want this to work. So if the bytes that you see in the file seem to be off a little bit by the number of bytes that are actually in your data structure, you either don't worry about that, or you start digging into finding exactly what the byte alignment pattern is being used in the IDE and what the settings are for that. So what I would like us to do right now is to make a customer array, all customers, and we only have 2. So I've allocated some space to read information back from the file. So what I want to do is get the customer data out of the file to prove that it's actually in there. And we're going to open the file for reading, and we will remember to close the file because I'll do it right now. And we're going to read all of the customers in the file at once. There's only 2 into this array, all customers. No ampersand because the name of an array is already an address, the address of where we want the data to go. And each one is size of customer, and we have 2 of them in there, and the customer file pointer is called customers. I'm going to set a breakpoint here, and if that compiles, we'll run to the breakpoint and see if in our array of customers called all customers we have Bob and Susan. So there's Bob owing us $24.56 approximately, and there's Susan owing us $345.99. And so this is the data that was read back from the file, from the binary file. So the rest of this specification, let's go back to the slides. You were going to create writing the customer objects using fwrite, and we did that, and then open the binary file and a text file. So as you read back the customers out of the file, use the customer data to create this report, and then you would have something that you would print. So the deadbeats report is the report of people who are in our customers file who owe us more than $100. And this should be kind of familiar from the segment we did on dynamic memory allocation. There was a function in there where we looked at all of the customers and printed out the ones that owed us a lot of money. So I'm going to leave that part of it to you, because this is a demonstration of reading data out of binary files, and we've achieved that in the example that we've been working on here. So in case you are flipping back and forth, I will let you look at this code again, and then let's go and have a brief summary of what we've been talking about in this segment. Okay, just a brief summary then of what we've looked at, and I'll probably remind you of the same thing that I've already talked about before. We were experimenting with reading and writing text and binary files. Don't mix them. If you're doing text input and output, only use the functions that are appropriate for that and open the file with the appropriate mode, and for binary as well. If you're doing text input and output of text files, keep reference copy of the format specifiers handy. You'll be tempted to guess, well, let's just try this one and see if that works. And the worst part of that is that sometimes it will work, but it will work for the wrong reason, and then later on your program won't work the way you expect it to. So if you do a lot of this, then you get to know exactly what the specifiers are. But as you're a beginner using text input and output, get a printed copy of the format specifiers if you're going to do anything that's at all interesting or complicated with text input and output. You should close your files as soon as you're done with them. So programs can only have so many files open at one time. If you're experimenting with reading and writing files and your program crashes in the middle, you might be using up the resources of the system and have to reboot the machine is the only way you can get them back. So if you're testing a program that stops before it closes the files, then you have to give back to the operating system the file handles. And if you're not doing that in the program using the fclose function, then eventually you will have to reboot the machine. So if your programs are crashing and then you can't do anything with files, it might be for that reason. If you're using binary files, draw a picture of the file format. Use graph paper and use each little square representing 1 byte. And don't guess. If you guess and do trial and error programming, it will just take you a whole long time. And it's an uncomfortable feeling to get a program working by guessing. You're not really sure or confident that it's working for the right reasons. So draw a picture of the file format, and it just makes your work a lot more pleasant. Okay, don't be afraid to play with this. Read a doc file and see what happens. And if the program crashes too much and you run out of file handles, reboot the machine. It's not going to hurt anything. So don't be afraid of trying to experiment with it and play with it. That's how you'll learn to be good at reading and writing files in C. I'll see you in the next segment.